Hello everyone, this is Wayne from the Chinese University of Hong Kong. I'd like to thank the organizing committee for the kind invitation and giving me this opportunity to share my work. The topic today is osteocytes, the missing link to abnormal bone mass in AIS and its clinical implication. AIS is a complex disease which is believed to involve the genetic factors and various environmental factors, leading to the onset and development of curve progression. The multifactorial nature of AIS complicates the development of specific and sensitive predictive model due to the involvement of complex cell-link pathways. Emerging evidence show that abnormal bone quality is closely associated with the progression of AIS. Our team previously reported low bone mass with defined access score of the femoral neck area BMD less than -1 with reference to the age, gender, and ethnic matched population in over 30% of those with AIS. Later, low bone mass was found to be an independent prognostic factor for predicting curve progression in AIS. The root cause of low bone mass in AIS is unclear. It is speculated and abnormalities of bone metabolisms in AIS possibly result in the spine being more vulnerable to deformity. This slide summarizes some key findings of the change of circulating bone metabolism markers in AIS. Bone histomorphometry studies on bone biopsies from surgical cases indicate the abnormally higher bone turnover in AIS. Interestingly, we observed more osteoblasts and less osteocyte number in AIS bones. Recently, we employed the time-lapse analysis on register high-resolution PQCT image to estimate local bone remodeling quantitatively. For the first time, we saw that progressive AIS had higher systemic bone turnover markers level and local bone remodeling. Association between disrupted bone turnover and the risk of the curve progressions is also indicated. The observation of abnormal bone metabolism in AIS is quite well received in the research field. Currently, research mainly focuses on the bone-forming cells, osteoblasts, and their progenitor mesenchymal stem cells. These two slides summarize some recent evidence in 2019 on the abnormal activities and differential gene expression in the primary osteoblasts and mesenchymal stem cell derived from the AIS bones, compared with the control group. Some of these studies provide quite comprehensive cellular mechanistic investigation and using state-of-the-art technology such as single-cell RNA sequencing. However, the clinical implication of this finding remain to be explored. So, why we are interested in the osteocytes? Osteocyte is the descendants of the osteoblasts. They are the longest living bone cells, account for majorities of the bone cell population. They are residing in the mineralized matrix canals, resulting in a lacunal canalicular network (LCN), which is a highly specialized ultrastructures for mechanical sensation and cell-to-cell communication. Change in the LCN connectivity has been reported in various schedule disorders. Until recently, it becomes more feasible to study the morphological changes of the osteocyte LCN. We have set up platform for the scanning electron microscope and the confocal physics image technique for qualitative and quantitative measurements of the osteocyte LCN, mainly their cell body, also known as the lacuna, and the dendrite protruding from the cell body, also known as the caliculi. In earlier crest bone tissues collected from AIS patients undergoing surgical correction and non-AIS control subject requiring orthopedic operation, we find disorganized alignment and distributions of the osteocyte lacunae, and some clusters of the abnormal osteocyte lacunae as well. At higher magnification, more details are revealed. AIS osteocytes tend to have irregular osteocyte lacunar morphology, shorter and disorganized calicula, and less cell-to-cell connectivity. Similar findings were also observed in all the collected AIS bone tissue and their control. Quantitative analysis by the PhysA image technique confirms our observation on the SEM image. In general, AIS osteocytes tend to have shorter and lower number of calliculi per their cell body, and their cells are more round in shape, indicating problem in differentiation. SEM and confocal imaging, although they can provide precise measurements of their structures, but they are not feasible to analyze massive number of the osteocytes. Therefore, in order to have a full pictures, we employed the nano-CT technology recently reported by a collaborator from Niederschulen to analyze over 300,000 osteocyte lacunae in the bone tissue from the deformed spine and iliac crest bone. This fresh evidence further supports our hypothesis of the abnormal osteocyte morphology in AIS and its association with the curve severity. After showing the presence of the abnormal structures of osteocyte LC and AIS, we next asked whether the molecular change leading to abnormal osteocyte in AIS could provide the hints on the environmental factors associated with the curve progressions. Culturing the human primary osteocyte is challenging. We developed an alternative method to differentiate primary osteoblasts into a osteocyte-like culture for molecular and functional experiments. Our recent study firstly revealed a causal relationship between the aberrant microRNA 145 expression and the abnormal osteocyte structures and function in AIS. The microRNA 145 expression inhibits osteocyte dendritic formation and function by disturbing the active beta-catenin expression and its transcriptional activity. Despite the source of the circulating microRNA being generally diverse, there are wide spectrums of the biological activity and the stable measurability in the plasma make them the potential biomarkers that can mirror systemic changes occurring in multifactorial disorders. Considering the involvement of multifactorial pathomechanisms of AIS, it is more logical to develop a composite model with clinically applicable and interpretable quantitative factors for predicting the probability of progression to severe levels. Here we propose a composite model consisting of clinical and circulating parameters for predicting the curve progression beyond 40 degrees at scheduled maturity. Two cohorts with a minimum of 6 years longitudinal follow-up were employed for establishing and validating the composite model. The ROC curve analyzes accuracy of the clinical parameters with the AUC. Compared with other single-factor, initial maximum curve angle had higher value of AUC of 0.87. Composite model had highest AUC value of 0.93, indicating the increased accuracy of the composite model when compared with our other individual factors. Data on the progression-free survival analysis were available for 120 AIS participants with the mean follow-up of 6 years, which shows that composite model offered significant prognostications with the hazard ratio of about 28. With the promising results from the previous investigation, the suitability and accuracy of the composite model were further assessed in a separate internal cohort with the same recruitment criteria. We proposed a composite model consisting of clinical and circulating parameters, which could quantitatively evaluate the probability of curve progression to the severe curvatures in AIS at the initial consultation. Using these two examples, you can see the patient with the risk score of 0.5 will progress to the severe curve, while the patient with the risk score at the initial visits is relatively stable. Of course, further validation with larger sample size in different ethnic groups is required. Take-home message: global mass is associated with AIS curve progression. Advanced time-lapse high-resolution PQCT image showed higher bone turnover in progressive AIS. Osteocytes, the major mechanical sensor in bone, might moderate asymmetric bone remodeling in the deformed spine. We propose a prognostic composite model with clinical and circulating parameters in assisting the objective clinical decision. But more importantly, can we alleviate the curve progression in AIS while targeting bone metabolism slowing pathways? Finally, I would like to thank all the patients and their families participating in this study and all the team members and my students and the research funding support. Thank you for your attention.